In this video, we'll be looking at the Fibonacci interview question in JavaScript. My name is Larry, and this is Digital Logic. To get started, you'll need to download the project from GitHub. The link is in the description below. I've also provided a linked introduction video to the series, which will walk you through setting up your development environment. With that out of the way, let's get started. So I've already got the project open in IntelliJ, so I'll open the project browser, and then open the fib.js file. For this challenge, you need to write a function that will produce the nth number within the Fibonacci sequence. The Fibonacci sequence is the following series of numbers. The next number is generated by adding the previous two numbers before it. Therefore, the nth number would be fib of n-1 plus fib of n-2. The following examples demonstrate the expected output for the provided input. Once you have a solution that you're ready to test, open up a terminal. In VS Code, the shortcut is Command tilde, and then type npm test fib, and then press enter. And as you can see, the current solution is failing the test. The testing framework will test any function that you export from the module.exports. So you can provide multiple solutions, and the testing framework will test all of them. So go ahead and pause the video now and try to come up with a solution to this challenge. When you're ready to continue, come back here and I'll walk through several different solutions. Welcome back. So I'll start by creating a new array named result. And I'll set the first two values to 0 and 1. And then I'll create a for loop. Let I equal 2, I is less than or equal to n, and then increment I. Now set result at I equals result at I minus 1 plus result at I minus 2. So at this point, the result array now contains the Fibonacci sequence up to and including the value of n. So now we just need to return result at n. Press Ctrl S to save the file, and then open up the console to view the test results. And it is passing the test. So the solution is very fast and efficient, but in order to compute the fib of n, we have to create an array of n plus 1 elements, when we really only need to know the last two elements in the sequence to compute the next. So for the next solution, I'll create a new function, and I'll call it FibOp. And then I'll add this function to the module.exports. Save the file, and then I'll open up the console to verify that this function is being tested. So now try to come up with a solution that's similar to the previous solution, except that it only requires to store the last two values within the fib sequence instead of an entire array. Welcome back. One way to solve this problem would be to create two variables, and then in our for loop, when we calculate the next value, we'd have to shuffle it in and one of the older values out. But I'm going to show you an easier way to do this. So I'll create a new array, result, and set the first two values to 0 and 1. Next, create a for loop just like in the last solution. I is going to be less than or equal to n, and then increment I. And now let's calculate and assign the next value within the result array. So result at I%2 equals result at 0 plus result at 1. The percent symbol is the modulus operator, and it returns the remainder of a division. So when I is even, the next value will be stored at position 0. When I is odd, the next value will be stored at position 1. This alternating of the index will ensure that we always overwrite the older value within the result array. Now we just need to return the Fibonacci value of n. So return result at, but which position? If n is even, we want to return position 0. If it's odd, return position 1. So let's use the modulus operator again, n%2. Save the file, and then open up the console to check the test results. And it is passing. So for the next solution, let's create a new function, and I'll call it recursive. Now the first step is to define the termination condition. So if n is less than or equal to 1, return n. And now return recursive n-1 plus recursive n-2. Make sure to add this function to the exports. Save the file, and then open up the terminal to check the test results. And it is passing the test. But before we get too excited about the simplicity of the solution, check out how long it took for the solution to run. The run times listed here are not super accurate. A difference of a few milliseconds doesn't mean one solution is faster than another. But in this case, the fib of 40 took nearly 1 second to execute, where in the other solutions, it was almost instantaneous. So we clearly have a massive difference in performance. So the question is, why is the recursive solution so much slower? And this is a subject I'll go into more detail with when I cover time complexity. But for now, the main reason is because the recursive solution does a lot of repetitive work. Every time the value of n increases by 1, the amount of work that the recursive solution has to perform doubles. So if I go back to the console to view the test results, we can see that the fib of 40 took nearly 900 milliseconds to execute on my computer, whereas the fib of 30 took 8 milliseconds to execute. So how can we create a recursive solution that isn't painfully slow? One approach is to use a technique called memoization, where we define an internal cache to remember intermediate values. Now that may sound complex, but it really isn't. So the first thing I'm going to do is comment out the recursive solution from the module exports. Now create a new function. I'm going to name it RecursiveCached. Now define the first parameter n, but then define a second parameter named cache with the default value of an array. And now create an if statement, if cache at n equals undefined. So all we're doing here is checking if we've already calculated the Fibonacci value of n. If this statement is true, then we haven't calculated it, so we'll do that next. So cache at n equals RecursiveCached n-1, and then pass in cache, plus RecursiveCached n-2, and then again make sure to pass in the cache. And now return cache at n. Make sure to add this function to the export list, and then save the file and open up the terminal to check the test results. And it is passing the test. All we're doing here is using an internal array to catch intermediate values so that we don't have to calculate them again. This does mean that the internal array will require n+1 elements in it, just like in the first solution. And unfortunately, there's nothing we can do about that requirement. For this last solution, I'm going to show you how you can externalize the catching mechanism so it doesn't have to be incorporated with the algorithm. So create a new function, and I'm going to name this one Memorizer. And it's going to take a single parameter as a function. Now create a new constant, catch equals new map. And now we're going to return a new function. I'm going to name it _memorizer. And then I'm going to collect all of the arguments into a single array, args. The 3-dot syntax within the parameter of a function declaration is called the rest parameters. And it allows a function to accept an infinite number of arguments as an array. Check out the Mozilla Docs for more info. And now create a new constant, key equals json.stringify, and then pass in the args array. Now we need to check if the catch contains this key. If it doesn't, then we need to set this key within the catch, and then we need to calculate the value for this key by executing the function and then providing it with the arguments. This time, the 3-dot syntax within the function call is called the spread syntax, and it's taking the arguments array and spreading them out as parameters to the function call. Check out the Mozilla Docs for more info. Now we just need to return the computed value. So catch.get and then pass in the key. Now let's put the memoizer to use. Create a new constant. Now I'm going to call this recursive memoized equals memoizer, and then pass in a new function. And this will be our recursive Fibonacci function. So first set the termination condition, and then return recursive memoized in -1 plus recursive memoized in -2. So all we're doing here is externalizing the catching mechanism to our memoizer function so that our core algorithm doesn't have to deal with it. Make sure to add the recursive memoized function to the exports. Save the file and open up the console to check the test results. And we can see that it is passing the test. Well, that is it for this video. If you liked this video, then please like, share, subscribe. If you want to support the creation of these videos, then check out my Patreon page. A link is in the description below, and I'll see you in the next video.